sample problems from section 16.3. Just to let you guys know ahead of time, there are 2 sample problems on this video, as pointed out right here. These 2 sample problems, I put them together because it turns out the second one's kind of short, so why make a really one? It was less than 5 minutes. So these are from section 16.3. The first problem is about 13 minutes long, and the reason why it's much longer is it goes over definitions as well as problems. You got to know what these things are asking for. It can get kind of confusing if you didn't go over them. So the first problem wasn't really that hard, but it's on using thermochemical equations. And the reason why it's the longer video is because it goes over definitions as well as the problem. The second problem is pretty much more straightforward. So it's actually less than 5 minutes long. And so you're going to see that we're in and out, except for there was a little bit of a typo in there that I speak of at the end, so it's not too confusing. And you know, hopefully these are helpful. So I'll put them both together in one video. In section 16.3, there are problems that deal with thermochemical equations and also energies of transformation, right? Melting, freezing, boiling, that stuff. So I'm going to do a couple sample problems here. So welcome. This first sample problem is going to be on using a thermochemical equation. Let's take a look and review what a thermochemical equation is. If you look here where I have the X, the plus sign over here, I have my question over here at the top. You have a chemical reaction. It says 2H2 plus O2 goes to form 2H2O. So hydrogen and oxygen are reacting to form water. This equation is balanced. That's why the 2's are there, because they're balanced. And it's a thermochemical equation because it has a delta H. And the delta H says delta H is equal to negative 285 kilojoules per mole. Now, we're going to talk about what that means right there, kilojoules per mole, in just a little bit. But let's read the question, and then we'll talk about that, and then we'll do the problem. So the question here says, give the delta H when 20 grams of H2 react with excess oxygen. So we're told we have 20 grams of hydrogen, H2, right over here. Question is, what is the delta H? Now, before I go ahead and do this, let me go ahead and first explain the whole thing about the kilojoules per mole. Because if you're observant, if you think about it, you might ask yourself, okay, so this reaction gives off 285 kilojoules. That's why there's a negative, because exothermic, it gives off 285 kilojoules per mole. But per mole of what? Is it per mole of hydrogen? Is it per mole of oxygen? Is it per mole of water? What is it? Well, this is going to be whenever you're given a delta H that says a certain number of joules or kilojoules per mole. What they're talking about is 1 mole, and do a couple things here. 1 mole of reaction. So 1 mole of reaction equals to negative 285 kilojoules. Well, what is 1 mole of reaction? 1 mole of reaction is when 2 moles of hydrogen react with 1 mole of oxygen to give you 2 moles of water. So whatever the number of coefficients you've got, that's how many moles of that each substance reacts during 1 mole of reaction. So 1 mole of reaction gives off negative 285 kilojoules. Now, how do you know if you've had 1 mole of reaction? Well, that's when 2 moles of water. So if you know how many moles of water, 2 moles of hydrogen, let's start with. 2 moles of hydrogen react. That's going to give off negative 285 kilojoules. Or when 1 mole of oxygen, the O2 has no coefficient in front of it, means it's a 1 mole. Right? 1 mole of O2 gives off 285 kilojoules. Because when 2 moles of H2 react, they react with 1 mole of O2. So the whole thing is going to give off negative 285 kilojoules. Now, you don't add these together. These are just telling you when 2 moles of hydrogen react, that's 285 kilojoules. When 1 mole of oxygen reacts, that's also negative 285 kilojoules. Because these two are happening together. You can't have 2 moles of hydrogen reacting without 1 mole of oxygen reacting. That's what this chemical reaction tells you, that these things are reacting together. So if you know how many moles of hydrogen reacted, you can figure out how much energy is given off, because you know that for every 2 moles of hydrogen reacting, you get 285 kilojoules given off. Twice as many moles of hydrogen reacting means twice as many kilojoules. 1/10 the number of moles of hydrogen reacting means 1/10 the number of kilojoules. So the number of kilojoules changes depending on the amount. This here is basically saying if 2 moles of hydrogen reacted, this is how much energy you would give up. Or if 1 mole of oxygen reacted, this is how many moles of energy would be given up. These two kind of go hand in hand. And when 2 moles of hydrogen react, 1 mole of oxygen react, and they form, according to this equation, the product is 2H2O, so that means we get 2 moles of water. 2 moles of water equals negative 285. So you'll notice that all these things here on the left equal the negative 285 kilojoules. You don't need to use them all. You're just going to use one of them. You'll notice here in this problem, we are given 20 grams of hydrogen. We're not told anything else. That's enough. Since we're given the grams of hydrogen, then we know that we got to figure out, okay, well, we're going to figure out how many moles of hydrogen there are. And then we'll use this relationship in order to do the problem. Okay? That's how you do these problems, right? And so it's real key to understand what this per mole means. Per mole here stands for mole of reaction. And that mole of reaction translates to each substance as the coefficient number of moles reacting. You do that with all of these guys. So see if I can get rid of some of these things in there. All right, so let me go ahead and clear this up here, and let's actually do the problem here. Let's try the scissors here. Better. All right. So now that we know what we're doing, we need to get moles. And once again, we need to know how to turn grams to moles. Okay, so we are given 20 grams of H2. In this case, we should get the pen and not eraser. With 20.0 grams of H2. That's the number we're given. And we're going to turn that into moles. And once again, to turn grams into moles, we have to go to the periodic table, look at the periodic table, and find that for hydrogen, our atomic mass is 1.01. H2, therefore, the atomic mass would be 2.02. That means 2.02 grams per mole. So 1 mole of H2 equals to 2.02 grams. And so what I'm going to do is I'm going to go ahead and put this as 2.02. 2.02 grams per 1 mole. For hydrogen, if I take 20 grams divided by 2.02, that I'm going to grab my calculator right now, and I am doing that right now. I take 20 grams divided by 2.02. That's going to give me 9.91 moles. So that'll give me 9.91 grams cancel, leaving me with moles. Now I know how many moles of H2 I've got. So I'll write that down. 9.91 moles of H2. And then I'm going to go ahead and multiply that by, well, the delta H is negative 285 kilojoules per mole, and the coefficient of H2 is a 2. That means that this reaction gives off 285 kilojoules for every 2 moles of hydrogen. So I can write this down. So I'm going to put 2 moles of H2 on the bottom. So that moles cancel. Looks like mine. And on top, I'm going to put minus 285 kilojoules. Because according to this, for every 2 moles of H2, that's minus 285 kilojoules. This left part goes on the bottom, so moles cancel. This right part goes on top, and it's going to tell us the number of kilojoules. Once again, the reason why this 2 is here, right here, because the coefficient of H2 is 2. If the coefficient of H2 had been 5, I would have put 5 moles of H2. I was still going to take this number of kilojoules on top here, but I'm going to divide it by the coefficient number of moles, okay? Because 1 mole of reaction has 2 moles of hydrogen, and 1 mole of reaction gives off this much energy. Now I can go ahead and do my calculations. And what I'm going to do is I'm going to take my 9.91 multiplied by negative 285 divided by 2, and that's going to give me my answer. And so I'm doing that right now with my calculator. 9.91 times negative 285 divided by 2 is going to give me 1,412. And you will notice that since we start off with a negative number, end up with a negative number. 1,412 moles cancel, moles of H2 cancel, and leaves me with kilojoules. And there is my answer. Okay, so when we're looking for our delta H, the reaction, then we're looking for kilojoules, and we need to have a quantity. Grams or moles of one of the substances would work. Okay, and so once you have moles, if you have grams, you have to turn to moles. We did the first step. If you already have moles, just plug it right in. And then using the delta H, the reaction, you go ahead and put the kilojoules on top and the coefficients number worth of moles on the bottom. One thing to note, and I don't know if I noted it earlier, was that this is the delta H, this is the delta H. Sometimes people get confused. Let me turn this to color. Get confused because they see 2 different delta H's, and they go, so Mr. Angulo, the question is asking for the delta H, but the delta H is right here. Can I answer it? They're different. This right here is a molar enthalpy. Notice I use the word molar enthalpy, and that's enthalpy per mole, right? A delta H per mole. This one is the total enthalpy, total delta H. How much are we getting total? Because we're not having just 1 mole react. It could have been 2 moles. It could have been a half a mole. It could have been a tenth of a mole. So this one takes into account not only how much per mole is given off, how much energy per mole is given off, but also the amount. So it's the total of amount, taking into account how much is given off per mole times however many moles you've got. Okay. Sometimes you'll get questions asking for delta H, and you're given a delta H as part of thermochemical equation. The delta H as part of your thermochemical equation is molar enthalpy. Molar enthalpy change, really. The delta H. Some people will put a little 0 at the top. You might see it like this. That tells you that's per mole. Just so you know, that is molar. Okay. Well, I hope that's helpful. Thank you for checking this out. Check out the second video coming right up. Hey, ladies and gentlemen, welcome back to sample problem number 2 from section 16.3. We are going to answer this question right here. This question says, how much heat is required to melt 50 grams of water. Delta H of fusion here, that's what you call this, is equal to 6.20 kilojoules per mole. So this one's pretty easy and straightforward. If you look at this, telling you basically heat of fusion is how much energy is required to melt something, and it's 6.20 kilojoules per mole. This is specifically for water, so all we have to do is figure out how many moles of water we have. We have 50 grams of water, so the first thing we got to do is turn our grams to moles. So just like we did back in chapter 11, we have 50 grams of, let me use a pen instead of an eraser. 50.0 grams of water. Multiply it, or at least divide it by the molar mass. For water, the atomic mass of hydrogen is 1.01. For oxygen, it is 16.0. I got these numbers from the periodic table. So two hydrogens and an oxygen. 2 times 1.01 and 1 times 16, add them together, gives you 18.02. 18.02 grams per mole. All right. So 50 grams turns out is, let me grab my calculator here. That's what I'm doing, is everything stopped. Is 50 divided by 18.02 gives me 2.775. 2.775 moles of water. Okay. Now I have moles. Now I can go ahead, since once again this is 6.20 kilojoules per mole, I can go ahead and take the number of moles, 2.770 moles of H2O, multiply it by 6.20 kilojoules per mole, and now your moles cancel here. And you take the 2.77 multiplied by 6.02. By the way, if you think 6.02 sounds like a familiar number, that is the coefficient from Avogadro's number, so we've been using that a lot. It turns out there's no relationship between this 6.02 and Avogadro's 6.02. It just so happens by coincidence that they're the same. Right? So I'm going to take my 2.77 multiplied by 6.02, and what I get is 5, right? 2.5 times 6.02 is going to give me 16.7. So I'm going to write here my answer, 16.7 kilojoules. Okay. And there's the answer. So when it comes to these transformations, and what I mean by transformation, I'm talking about melting, phase changes, basically, boiling, freezing. Hey, there's one on sublimation also, called the heat of sublimation. We really didn't talk about it, but it's out there. Whenever these things are occurring, the problems are real easy. They'll just tell you how much energy it takes per mole. You just find out how many moles of substance you have that want to freeze or boil or melt. And then once you have the number of moles, you just multiply it by the your heat of fusion. Or heat of fusion is for melting and freezing. And if you want boiling, you'd use heat of vaporization. And then you multiply them together, and there's your answer. Pretty straightforward. Important thing is that you look at these and go, okay, kilojoules per mole. So it's 6.2. Sorry, that was a typo. That should be 6.0. Typoed it. In case you were confused during the video, why is she putting 6.20? The typo would be there. It's supposed to be 6.02. I know, because as I mentioned, it's the same number as that on the coefficient of Avogadro's number. And I guess when I was typing it out, I inverted the numbers. But yeah, no big deal. As long as you kind of know how to do this, you just multiply by your heat of fusion or your heat of vaporization, That'll get you your energy, joules or kilojoules. In this case, it was already kilojoules. Okay. All right, so hopefully it's helpful. It'll help you for some of the problems on the homework.